Hello everyone, welcome to quick revision series of strength of materials. In this video, we will be discussing about shear force diagrams and bending moment diagrams. The video begins with a small introduction. Next, we will be seeing some shear force and bending moment diagrams of standard loadings. I will be explaining in detail how to draw shear force and bending moment with two different loadings. And lastly, I will be explaining some concepts which are frequently asked in exams. Now, let's know the definition of shear force and bending moment in brief. If we consider a beam, if shear force at this particular section XX is asked, if we take this part of the beam, there is a reaction force acting P by 2 acting in upward direction. In order to compensate this reaction force, there must be some internal force acting in downward direction. This is nothing but the shear force at that particular section. Similarly, there is a reaction force acting here and there is a force acting here in downward direction. That means there is a couple generating here on this part of the this part of the beam. So in order to compensate this couple, there must be a bending moment, there must be a moment acting in anti-clockwise direction. This is nothing but the internal reaction generator, and which is nothing but the bending moment acting at that particular section. Now, mathematically, if we see the definition of shear force and bending moment, like how we calculate the shear force and bending moment at a particular section, we generally take a section and consider all the forces which are acting either to the left of the section or to the right of the section. While calculating the bending moment, we will be considering all the moments generated due to the forces either to the left of the section or to the right of the section. Now, let's see the sign convention part. At a particular section, if the load is acting to the right and in the downward direction, it is considered positive. And if the load is acting in upward direction and to the left of the section, it is considered as positive. This looks confusing. Now, I will say a trick so that you can remember it easily. If the given load, if it generates a clockwise moment, then that shear force is considered as positive. If that load generates an anti-clockwise moment. So, see, if you consider this load, this is generating an anti-clockwise moment. So, this shear force is this load is considered as negative, like negative shear force. So, in detail, like if we consider a beam P by 2, now, without confusion, let's see this at this particular section. If shear force is asked, this load is generating an anti-clockwise moment. That means this should be considered as negative shear force. If we consider this load, this is generating a clockwise moment. So this shear force is considered as a positive shear force. Now let's see the sign convention for bending moment. Let's consider a beam. This is an anti-clockwise moment acting on this. See, if we take this beam, this anti-clockwise moment is generating like this. Because of this anti-clockwise moment, the beam bends this way. And because of this clockwise moment, the beam then bends this way. This is creating a sag in a beam. That means if a particular moment bends the beam such that it generates a sag, then this moment is considered as positive. And if a particular moment bends the beam such a way that it generates a hog, that moment is considered as negative. Simple way in remembering is sag, smile, sag and smile, S and S, and smile is a positive indication, so positive bending moment. Similarly, hog is a negative, hog is negative bending moment. Now let's discuss some relations between shear force, bending moment and load intensity. These definitions are directly asked in some exams, or these definitions are used in SFD and BMD diagrams. And in some questions they'll be giving a shear force and they'll be asking find the bending moment at a particular section. These definitions are directly or indirectly asked in exam in some manner. Now let's see this. According to this, the slope of shear force diagram gives the intensity of load. The slope of bending moment diagram gives shear force. Okay, and in order to, like, if we consider this thing, we'll be getting this, like, see, we know that integral of S dx is nothing but area under shear force diagram. That means if we are given like the shear force diagram of a particular beam, if we are supposed to find the bending moment at a particular section, we can calculate by using this. If we find the area of a shear force diagram for, like between 2 points, then difference in moments between those 2 points gives us, is nothing but equal to the area between those 2 points in SFD diagram, like shear force diagram. Now here we will be seeing what's the type of load and how its SFD looks and how its BMD looks. If we have a point load, like if we consider this beam, cantilever beam, there is a point load. If we have a point load, then shear force will be a rectangle and a bending moment will be triangle. Triangular variation is nothing but a linear variation, and this is a 0 degree variation. Now let's see the for uniformly distributed load. In case of uniformly distributed load, the shear force diagram will be linearly varying and bending moment diagram will be parabolically varying. And in case of uniformly varying load looks like this. In case of this, the shear force diagram will be a 2 degree parabola and a bending moment diagram will be a cubic parabola. If the loading is a 2nd degree variated loading, then shear force diagram will be cubically variated diagram and bending moment diagram will be 4th degree variating 4th degree equation. For an nth degree varying load, the shear force diagram will be n plus 1th degree varying varying curve, and bending moment diagram will be n plus 2th degree varying curve. Now let's proceed to next part. In this case, we will be knowing what is meaning of point of contraflexure and what is point of inflection. Point of contraflexure is nothing but the point at which the bending moment changes its sign. See here, the bending moment is changing from positive to negative. This point is nothing but point of contraflexure. In exams, we will be asking find the distance from some certain support where the point of contraflexure occurs. In this case, we can find the point where bending moment is 0. We can find that point is nothing but point of contraflexure. What is point of inflection? This is nothing but the point where curvature changes. See, in this case, if we consider this point, here it's sag and here it's a hog. At this point, the curvature is changing from sagging to hogging. So this point is known as point of inflection. In case of beams, both are same. See, the point where bending moment is 0, there the point of inflection occurs in case of beam. Now let us discuss some more points. The point where shear force changes its sign, bending moment will be maximum. See here, the shear force is changing from positive to negative. At this point, bending moment is maximum. This point looks simple, but this will be helpful in solving problems. See, when in some questions they will be asking what is the location of maximum bending moment. In case of if we go mathematically, we should write the bending moment equation, and we should know, for knowing the point where the maximum bending moment occurs, we have to differentiate it and make it equal to 0, and we should find the x equals to something, and after finding that we will be knowing. In order to make it simple, like we can find the point where shear force is 0. Like we can easily write the equation of shear force. The point where shear force is equal to 0, we can directly say that point is that point is of maximum bending moment. After knowing that point, we can substitute this in the, we can substitute that point in bending moment equation and find the magnitude of bending moment also. Now, next point is where there is a concentrated load, there is a jump in shear force diagram, and where there is a concentrated moment, there will be a jump in bending moment diagram. Now, let's see this. See, let us consider this beam. In this case, there is a reaction force here P by 2, a concentrated load P, and reaction force P by 2. If we look the shear force diagram of this, there is a jump here. If we see this, because of this concentrated load, there is a jump generated here. Because of this concentrated load, there is a jump generated here. And because of this concentrated load, there is a jump here. So this point, I think this point is clear now. See, now here, if we observe, there is a concentrated movement here. Because of this concentrated movement, there will be a jump in bending moment diagram. Okay? And I'll be explaining other points. See, the difference in magnitudes of shear force or bending moment at a point where concentrated load occurs gives the load or a moment at that point. See, if we consider this point and this point, plus P by 2 minus of P by 2, which is equals to P. That means difference between these two, difference between the shear force at this here and here gives us the magnitude of load itself. Similarly, in case of bending moment. I hope you understood this. Now, let's see shear force and bending moment diagrams of some standard loading. Here, in this case, there is a concentrated load acting on at the center of the beam. This is a simply supported beam. This is hinged support and this is roller support. I think you all know this. So, there is a concentrated load acting at the center of the beam. In this case, shear force diagram looks like this and bending moment diagram looks like this. And we should remember this: in case of concentrated load acting at the center, the maximum shear force will be at the center and its magnitude will be PL by 4. Same way, this thing. See, the reaction, if you want to calculate the reaction acting at this point, see, this reaction will be, this load is P into, we are writing reaction at this point. Then we have to consider this part of the beam. This is shortcut so that it will be easy. The normal procedure to find reaction is making moment at that point is 0. To make it simple, if we can remember this way, in order to calculate reaction at this point, we have to consider this P into dimension here A by L. Okay. So these two are the reaction forces here and here. The shear force diagram looks like this. And we have to remember this. The maximum bending moment acting on this particular beam is P into AB by L. I think you know this. If you substitute A and B equals to L by 4, L by 2, you will be getting PL by 4. In this case, it is uniformly distributed load and the shear force is linearly varying and bending moment is parabolically varying. We discussed this a few minutes ago. This is uniformly varying load. In this case, the reaction here is WL by 6 and the reaction here is WL by 3. If you are confused, see, here there is a maximum intensity. So, the reaction at this side will be maximum. So, WL by 3, which is double the reaction here. And the maximum bending moment will be WL square by 9 root 3. This will be acting at a distance of L root 3 from this support. Let's see the shear force and bending moment diagram for a cantilever beam. There is a concentrated load acting at the end of the beam. Then shear force diagram looks like this and bending moment diagram looks like this. When there is a varying load, shear force diagram looks like this, bending moment diagram looks like this. So let's see how to draw shear force diagram and bending moment diagram for a particular beam. In this case, we have a simply supported beam with a uniformly distributed load and we have to draw SFD and BMD. The first step to follow is finding reaction. In order to find the reactions, here in this case we consider the sum of all the vertical forces equals to 0. So if we consider RA and RB are the reactive forces, then sum of RA and RB equals to total load acting. Total load acting is W intensity of load into length of load. So we get this, and in order and the second one I used is moment at A is 0. This is hinged support. There won't be any moment at hinged support. So MA equals to 0. Considering MA equals to 0, we will be getting considering MA equals to 0, we will be getting a reaction RB as WL by 2. If RA and RB as we know that RA and RB is WL, so we will be getting RA equals to WL by 2. Next, this second step is we have to select a section. I have selected a section XX. At this particular section X, if we write the shear force, shear force at this particular section, this will be equals to RA minus WX. RA is the upward reaction acting and WX is the total load acting. This is a section. So considering this, we will be getting shear force as RA minus WX. Now in order to find the shear force at A, we have X is equals to 0 because X we have taken from A. If we make X equals to 0, the section will be exactly at A. So for shear force at A, if we substitute X equals to 0, we will be getting shear force at A as RA, which is equals to WL by 2. Similarly at B, by substituting X equals to L, we will be getting shear force at B as minus WL by 2. And at C, that is at the distance L by 2, we will be getting shear force as 0. So we can see at A we got shear force as plus WL by 2. At B we got shear force as minus WL by 2. At C we got 0. Joining this, we will be getting shear force diagram. This is detailed procedure which we can't do in competitive exams. Now let's see a simple one. See, this is uniformly distributed load. That means reactions will be half. Directly we can calculate the reactions and write WL by 2. Now we know that when there is a concentrated load, there will be a jump in shear force diagram. Now at B, there will be jump in shear force diagram from 0 to value of the reaction at this at B. Now how to know whether we have to take it negative or positive? Now if we consider this section, this is generating an anti-clockwise moment. We have seen the sign convention thing. If that force is generating an anti-clockwise moment, we consider it as a negative, negative shear force. So this is negative. So we have this point. Next, if we consider section here at A, this is generating a clockwise moment. That means the shear force here is positive, and we have this point WL by 2 here. So if we join these 2 points, we will be getting a shear force diagram. Indirectly, we will be getting a point C, which is where the shear force is 0. Similarly, while calculating the bending moment, we will be considering writing the equation for bending moment at the distance x. So we will be getting this equation. For bending moment at A, we will be substituting x equals to 0. For bending moment at B, we will be substituting x equals to L. For bending moment at C, we will be substituting x equals to L by 2. And this is the standard procedure. We know that at point of 0 shear force, there will be maximum bending moment. So directly after writing this equation at C, we can calculate by substituting x equals to L by 2, we will be getting maximum bending moment. So the maximum bending moment we will be getting as WL square by 8. And we know this support is a hinged support and this is roller support. At hinged support and roller support, there won't be any bending moment. So directly this will be 0. And this is uniformly distributed load. For uniformly distributed load, shear force diagram will be a linear varying one and the bending moment diagram will be a parabolically varying one. By joining this, we will be getting a bending moment diagram. Now, some people may have doubt like, we know that it's a parabolic variation, so can't it be this way? First thing, bending moment diagram doesn't have a sharp edge, because we know that slope of bending moment diagram gives us shear force. See, if we have a sharp edge, the slope, we have two slopes. That means at this point we have two shear force, which is not possible. So this type of diagram is not possible. And I'll be discussing in some short video like how should we consider the type of variation, like this way or this way, how to consider it. I'll be explaining in short in other video. Now let's take the second example. This is the normal procedure we follow in order to calculate the shear force and bending moment at particular sections. Now let's see the easy way, to draw the shear force and bending moment diagram. For any way, we have to find the reaction forces at A and B. For finding the reaction forces, this equation I consider, that is sum of all the vertical forces equals to 0 and the moment at A equals to 0. For considering moment at A equals to 0, I considered anti-clockwise as positive and clockwise as negative. See, RB into L. RB I consider it as an upward reactive force acting. RB into L plus 2m is in anti-clockwise direction, which is considered positive, and clockwise moment is considered negative. By calculating, by solving this equation, I will be getting RB as minus m by L and RA as plus m by L. That means RB is this way and RA is this way, plus m by L. So now we have to now we have to draw shear force diagram for this. See, in this case there is no vertical forces acting on the beam. There are only two reactive forces which are acting. This reactive force is in downward direction with magnitude m by L, and this reactive force is in upward direction with magnitude m by L. Now we know that when there is a concentrated load, there will be a jump in shear force. Jump in shear force diagram. See, now considering this load is generating a clockwise movement. That means shear force is considered positive. Okay. Similarly, this load is generating a clockwise movement. So shear force is considered positive. So shear force diagram looks like this: a triangle with m by L as a height and L as length. Now let's draw the bending moment diagram. For drawing the bending moment diagram, we know the the bending moment at hinged support and roller support is 0. Okay. Next, we have to find bending moment at C. For finding bending moment at C, bending moment at C will be equals to RA into L by 3. This is generating a sag, so this will be positive. RA is m by L into L by 3. So bending moment at C will be m by 3. This m by 3 is just to the left of the section C. Okay, because there is a concentrated load acting, concentrated moment acting on the beam, there will be a jump in bending moment diagram. So just to the left of the section, the bending moment will be m by 3, and for calculating just to the right of the section, we have to consider RA into L by 3 plus m, which is equals to 4m by 3. Okay, 4m by 3. Okay, we know some other point also. The difference in bending moments at this point and this point is equals to the concentrated moment acting. Okay, similarly we can find for B also. The the bending moment at D is minus m by L into L by 3. We will be getting m by 3. M by 3 plus, m by 3 is acting in anti-clockwise direction, and plus 2m is also acting in anti-clockwise direction. By adding, we will be getting 5m by 3. This is 5m by 3. We know after finding all this, we will be joining this, then we will be getting bending moment diagram. Now let's see some examples which are frequently asked in exam. Here in exam they will be asking number of contraflexures for a particular beam. They will be giving some length here and some length here and some length here. If they ask number of points of contraflexure, we can easily find it this way. If L is greater than 2A, we can directly say there are 2 points of contraflexure. If L equals to 2A and L less than 2A, there are 0 points of contraflexure. Remember, for L equals to 2A, there are 0 points of contraflexure. See, this point is not point of contraflexure because here the bending moment is not changing from positive to negative. Okay, remember this, don't confuse. Okay, this is generally asked in exams. Like if you want a detailed explanation and how we achieve this, I'll be explaining it if you want it. Okay, now let's see this one. In this case, in some questions they will be asking for maximum bending moment to be least possible, find the relation between what is the length of overhang, or find the relation between A and L. They will be asking this way. In this first case, the value of A will be 0.586 times of L. I got this 0.586 by simplifying 2 minus root 2. If you want, even if you want this in detail, let me know. I'll be uploading it in a short video. So for this to be possible, we'll be considering this. Like for maximum bending moment to be least possible, the positive bending moment should be equals to the negative bending moment. See, I'll be calculating in this case. In this case, the negative bending moment the negative bending moment will be WL dash square by 2. And the positive bending moment will be, we know that maximum bending moment is WL square by 8 minus WL dash square by 2. See, the maximum positive bending moment is equals to the maximum negative bending moment. By simplifying this, we will be getting L dash equals to L by root 2. Remember these values directly. This thing you can derive it, but deriving this takes time, so remembering this will be helpful. These are some concepts in SFD and BMD. I found it useful for competitive exams. If you want some more concepts to be explained, let me know. If you find this video useful, share it with your friends. Thanks for watching.